leave. I won't be offended. Okay, so today I'm going to talk about our work on parallel batch dynamic K-core decomposition. This is joint work with Quan Liu, Jessica Shi, Shamdi Yu, and Lakshman Duapala. You've heard a little bit about this work in Quan's talk earlier in this workshop, but I'll provide some more details and also go over some experimental results. It seems like the clicker's not working. Okay. So first of all, graphs are becoming very large today. The largest publicly available graph has over 100 billion edges. And this graph represents just a small fraction of the websites on the internet. And there are proprietary graphs out there that are even larger with orders of trillions of edges. Furthermore, many real-world graphs are rapidly changing, as we all know. For example, on the Twitter network, there are about 500 million new tweets per day. And on the internet, there are over 500,000 new websites created every day. And these events correspond to updates to our graph. So in order to process these massive and dynamic graphs, we use parallelism as well as dynamic algorithms. So we want to design algorithms that can take advantage of the multiple processing units on almost all modern machines today. And of course, we want to design dynamic algorithms to avoid unnecessary work on these updates. So our work focuses on this parallel batch dynamic setting, which you've heard several times already. But just as a reminder, in this setting, we're getting our updates in batches, and we can use parallelism within each batch to speed things up. Okay, so pictorially, we're getting batches of edge insertions and deletions. You can also deal with vertices, but I'm just going to talk about edges for this talk. We also have a current graph as well as some statistics we want to try to maintain about the graph, such as the triangle counts, the page ranks, and so on. And we want to be able to efficiently generate this updated graph as well as the statistics, updated statistics. So we want to delete the edges that we don't want anymore. We want to add the edges that we want, and then we want to update our triangle counts or page ranks efficiently. Okay, so we've looked at a variety of problems in this parallel batch dynamic setting. Most of these are graph problems, but we've also looked at the closest pair problem, which is a problem from computational geometry. And for all of these problems, we were able to come up with theoretically efficient algorithms in terms of how much work they do and how much parallelism they have. And for some of these problems, we also implemented them and showed that they run efficiently in practice on modern machines, on real-world data sets. So today I'm going to focus on one of these results, which is the K-core decomposition result. I do want to mention that there has been a bunch of related work on designing algorithms in this parallel batch dynamic setting. So people have looked at triangle counting, Euler-Tour trees, connected components, rate compressed trees, as well as incremental minimum spanning trees. And some of these papers include Guy Blalock and Lakshman Duapala. They're not here, but they told me they're going to be watching the stream, so I made sure to put their citations. Okay, so let me define the K-core decomposition problem. So a K-core in the graph is a maximal connected subgraph such that all the vertices have induced degree at least k. So if we only consider the neighbors that are in the subgraph, we want to have at least k neighbors. And the coreness of a vertex v is the largest value of k, such that v participates in the K-core. So in this example graph, these four vertices that I've circled here are in the 3-core. You can check that they all have induced degree at least 3. And furthermore, if I added any other vertex to this 3-core, any other subset of vertices, it would no longer be a 3-core. Somebody would have degree less than 3. Now, all of these vertices in the bigger blob are in the 2-core. Again, you can check everyone has degree at least 2. And if I were to add this last vertex to this 2-core, it would no longer be a 2-core because this last vertex has degree 1. And finally, the entire graph is in the 1-core. And now the coreness of that vertex v that I've labeled is 3. It participates in the 1-core, 2-core, and the 3-core, and 3 is the largest value of k. So the goal of this problem is to compute the coordinates values for all the vertices in the graph. Once you have the coordinates values, you can easily extract a k-core for a particular value of k just by running connected components on the appropriate subset of vertices. Any questions about the definition? Okay, so it turns out that exact k-core decomposition is pretty hard to parallelize. And furthermore, in many applications, you don't really need an exact k-core decomposition. So we decided to look at this approximate k-core decomposition problem. So the definition of k-core is still the same. It's just that these coordinates values we return are approximate. So we return these C approximate coordinates values where the values are within a multiplicative C factor of the true coordinates. Okay, so let's say I assigned a coordinates value of approximate coordinates value of 3 to everything in that gray blob, and then approximate coordinates of 2 to that last vertex. Then the 3 yellow vertices would have a 3/2 approximation because their true coordinates is 2, and I gave them an approx coordinates of 3. And then the green vertex has a 2 approximation because I gave it an approx coordinates of 2, but its true coordinates is 1. Okay, so our goal is to try to maintain these C approximate coordinates values for appropriate value of C. Yes, question.
So in the offline setting, if you just remove the minimum degree vectors, does that give you the optimal?
Yeah, so that's a good question. So the question was in the offline setting, how do you solve this problem? So it turns out that in the offline setting, there's an easy peeling algorithm, as you suggested, where you just repeatedly delete the vertices with the minimum degree. And when you delete the vertex, like whatever value of k you're looking at, when you delete the vertex, then you assign a coordinates of k to that vertex. And then if there are no more vertices with degree at most k, then you increment k and then you repeat until the whole graph is empty. Yes?
So is k-core decomposition unique?
Is it unique? Yeah, so everybody has a unique core number, coordinates value. Yeah.
Yeah. Are you allowed to err in both directions when you consider approximation?
Yeah. So this is a two-sided approximation. Yeah.
What approximation does it get?
The peeling algorithm solves it exactly, but it's not parallel. It's not theoretically parallel because there are certain graphs where you just have to peel for a linear number of rounds, and then you don't get any parallel speed up. For example, if you just imagine like a chain, like the two end vertices have degree 1 and everyone else has degree 2, then you just keep peeling off the two ends of the chain, and you need a linear number of rounds. Yeah.
Is there no known parallel algorithm for it?
Well, the getting better than a 2 approximation for exact k-core is, well, okay, getting better than a 2 approximation for k-core is p-complete. So there's a proof showing that like it's very unlikely that you can get better than a 2 approximation, assuming some complexity results.
It is known.
Yeah. Okay, good. So I'll just briefly mention some of the applications of k-core decomposition. So for these applications here, they're actually using k-core approximately anyway, so it's reasonable to plug in an approximate k-core algorithm. So graph clustering, community detection, some of them use coordinates values. Graph visualization, this is a pretty intuitive example, so you want to basically be able to zoom in on appropriate parts of your graph. Like if you want to look at a dense part, then you zoom in there, and then a k-core decomposition will allow you to do that efficiently. But this task is approximate anyways, so it's fine to use an approximate decomposition here. And then there are some other applications like protein network analysis and approximating the network centrality. Okay, so the model that we're going to be using to design and analyze our algorithms is this work span model of computation. So here the work is the number of operations your algorithm does, and the span is the length of the longest sequential dependence. And if you are able to get a work in a span bound, then you can upper bound the running time of your algorithm by the work divided by the number of processors plus big O of the span. And this running time can be achieved using a randomized work stealing scheduler, so you get this runtime in expectation. If you use a greedy scheduler, you can actually get rid of the big O in front of the span, but greedy scheduling is not practical, so nobody uses that. Okay, so our goal is to come up with low-span parallel algorithms that are also work efficient. So work efficient means that the work of the parallel algorithm asymptotically matches the best sequential algorithm for the same problem. So we care about low span, obviously, because we have the span term in the running time. But we also care about work efficiency because there's also a work term in the running time. And in practice, if you have an algorithm that's reasonably low span, like polylogarithmic, or even n to the epsilon for some small epsilon, then the first term, work over number of processors, is going to dominate, assuming you're processing large data sets. But that's a reasonable assumption because otherwise you wouldn't need parallelism. So therefore, in practice, the work divided by number of processors is usually going to dominate if you have a reasonably low span. So that's why we want to try to reduce the work as much as possible. And the best you can do, at least asymptotically, is to match the sequential algorithm. So I'll give a summary of the results that we're able to achieve. So we're able to get a parallel batch dynamic algorithm that maintains a 2 plus epsilon approximation for the coreness of every vertex. We show that a batch of B updates takes order B log squared n amortized work and polylogarithmic span with high probability. And the algorithm's work efficient because the best sequential algorithm for this problem takes order log squared n amortized work per update. And we're doing B updates in order B log squared n work. Okay. Our algorithm is based on a parallel level data structure, which I'm going to spend some time talking about. But before I do that, I want to mention the sequential level data structure, which I'll abbreviate as LDS. And this sequential level data structure was described in previous work by Bhattacharya, Hensinger, Nanonkai, and Tsourakakis, and then also in another paper by Hensinger, Newman, and Weiss. So in this data structure, the vertices are partitioned into order log squared n different levels. These levels are further grouped into groups of log n levels, order log n levels each. And what we want to do is we want to maintain certain invariants per vertex. And these invariants have to do with the up neighbors of a vertex. And an up neighbor of a vertex is roughly defined to be the neighbors of the vertex at its level or above in the data structure. There's some technicalities which I don't want to get into, but basically you can just imagine the up neighbors to be vertices at the same level or above it in the level data structure. And the invariants say that we need to have some upper and lower bounds on the number of neighbors, up neighbors that each vertex has. So it can't have too many, but it also cannot have too few. And these thresholds are going to be based on the group that the vertex is on. So each group has a different cutoff that we're going to use for these upper and lower bound invariants. Okay, so later on, I'll talk about how these group numbers translate to good Coreness estimates, but I'm just going to put that aside for now and tell you how the level data structure works. Okay, so when your graph gets updated, some of these invariants for certain vertices could be violated. So if I add this red edge, the yellow vertex now might have too many up neighbors. And in order to fix that, I'm going to move the vertex up so it loses that up neighbor, and then now maybe it's happy it doesn't have too many neighbors. And the same thing can happen when you delete an edge. So if I delete this dashed red edge, the yellow vertex could now have too few up neighbors. So then I'm going to keep moving it down until it has enough up neighbors to satisfy the invariance. So that's basically, at a high level, how the sequential level data structure works. The actual implementation requires you to modify some data structures efficiently, but I'm going to sweep those details under the rug. Okay, so there are some challenges with parallelizing the sequential level data structure. The first is that there could be these large sequential dependencies. So there could be these chains of movement. So let's say I move that yellow vertex down after I delete the red edge. It could actually cause its neighbor to now have too few up neighbors. So then I need to move the neighbor down as well. And then that neighbor is going to cause its neighbors to move down. And then we get this chain effect where everybody is basically moving down one at a time. And this is not good for parallelism it leads to an algorithm with large span. And then the second challenge is, well, the sequential algorithm by definition is only processing one update at a time. But if we have a batch of updates, we want to try to do better than processing each one at a time. So those are the two things that we're going to try to fix with our parallel version of the level data structure. Any questions? Okay. So our parallel level data structure, which we call PLDS, supports batches of edge insertions or batches of edge deletions. I'm going to focus on edge deletions. Insertions are similar, but not entirely symmetric, and Quan did talk a little bit about insertions in her talk. So I'm going to focus on deletions. Okay, so the first thing to notice is that when I delete edges, only the lower bound invariant can be violated. So when I delete edges, vertices could lose up neighbors, but they can never gain any. And therefore, I only need to move vertices down to make sure that their lower bound invariant becomes satisfied again. I never need to move them up. Okay, so what we're going to do is for all of the vertices that are incident to these edges that I delete, I'm going to check whether their lower bound invariant is violated. If they are, then I'm going to compute what's called a desire level, which is the closest level below them that they're such that their lower bound invariant is satisfied. So in this example, let's say the 3 yellow vertices are no longer satisfying their lower bound invariant. So I computed this desire level for these 3 yellow vertices. So the desire level is basically the closest level below that satisfies invariance. So the 2 yellow vertices on level 7 now want to move to level 5. And then the yellow vertex at level 10 wants to move to level 8.
But is that if you're moving them individually without looking at anything else?
Yeah. So the question was, is this the desire level, assuming you don't move anything else? And the answer is yes. So that's why after we move some of them, you need to possibly recompute these desire levels. Okay, so the algorithm is going to iterate from the bottommost level to the top. And then for each level that it looks at, it's going to see if anybody wants to go there. So the first interesting level here is level 5. There are 2 yellow vertices I want to go there. So we're going to move them down to level 5 in parallel. We don't want to do them one at a time because we want parallelism. And after we move them down, they could actually now cause some of their neighbors to no longer be happy. Or if one of the neighbors already had a desire level, maybe we need to update that. So for this example, let's just say that this yellow vertex, the one on the left there, before it was happy, but now it's not. So now I compute a desire level for it, which is going to be 6. And then let's say the other yellow vertex, which had a desire level of 8, I'll just keep that. So now when I get to level 6, I'm going to move the yellow vertex at level 8 down to level 6. And I'm going to check whether its neighbor, its remaining up neighbor wants to move down. For this example, let's just say it doesn't. Then when I get to level 8, I'm going to move that last vertex down. So now let's assume everybody has satisfied their lower bound invariant, and I'm done. Okay, so in the deletion algorithm, every vertex is going to move just once. It's going to move once to its to the final desire level that it wants to go to. This is different from the sequential LDS, where if you were processing the updates one at a time, each of the updates could cause a vertex to move down one level. But for us, for a single batch, each vertex is going to move down just once to its final level. Okay, so let's go back to the question about estimating these Coreness values. So we set the Coreness estimate of a vertex to be 1 plus delta to this messy expression, which you don't need to fully understand, but this exponent of the 1 plus delta is roughly equal to the group number that the vertex is in. So recall that we basically partitioned our levels into log n groups, each of order log n levels. And the exponent there is roughly which group the vertex belongs to. Okay, so what this means is that vertices that are higher up in the data structure will have higher Coreness estimates. And intuitively, this sort of makes sense because a vertex needs to be high up if it has many neighbors who are also high up. And then if you look at the k-core problem, vertices that are in a k-core for a large value of k, they have to have a lot of neighbors who also have degree at least k. So that sort of corresponds to our intuition that the vertices high up in this data structure are likely to be a part of these dense cores. Okay, so we show that using this Coreness estimate equation, you get a 2 plus epsilon approximation. I'll give some intuition about how you prove the upper bound for this approximation on the next couple of slides. And it turns out that getting better than a 2 approximation is p-complete, meaning that it's unlikely you can get a low span parallel algorithm. And this is because the static problem for k-core is p-complete. Getting better than a 2 approximation is p-complete. And if we can get a dynamic algorithm that does better than 2 approximation, we can just use that to solve the static problem by giving all of the edges as a single batch. Okay, so let me give some intuition about the upper bound proof. So first, we need to think about this peeling process, which I mentioned earlier. So if you're trying to solve the k-core problem statically, you're going to have this variable I, and then you're going to delete this variable I starts at 1. You're going to delete all vertices with degree at most I. You repeat this process until there are no more such vertices, and you increment I to I plus 1, and you repeat. And then eventually the whole graph is going to get removed. And the time when you remove a vertex, if it gets removed in this round I, then you assign it a Coreness value of I. So that's how the static algorithm for k-core works. Okay, so recall that we set the Coreness estimate of a vertex to be 1 plus delta to the I, where I is roughly the group number. But also recall that we had these upper and lower bound invariants. So in particular, the upper bound invariant says that you cannot have more than 2.1 times 1 plus delta to the I up neighbors. And 2.1 here is not very important. It just has to be some constant bigger than 2. Okay, so let's look at this yellow vertex here and imagine the peeling process. So if I'm peeling the vertices from the graph, well, I'm going to get rid of the ones that are lower down first. And then eventually, I'm going to get rid of all of the neighbors of the yellow vertex that are below it. And then when I peel off this yellow vertex, by definition, its core number is going to be upper bounded by its up degree at this point. But we also have that the up degree is upper bounded by 2.1 times 1 plus delta to the I. So therefore, we also get that the core number of this yellow vertex is upper bounded by 2.1 to the 2.1 times 1 plus delta to the I. We gave it an estimate of 1 plus delta to the I, so this is a 2.1 approximation. It's just one-sided. If you want to prove the other side, meaning that you want to show that the true core number is not too much smaller than the estimate, the proof is more complicated, but it also uses this peeling process. So the high-level idea is that assume that the core number was way smaller than the core. The true core number was a lot smaller than the estimate the algorithm gave. Then we can sort of do this peeling process, and then we peel off vertices, and it turns out that before we get to the yellow vertex, the whole graph is gone, and this leads to a contradiction. So I'm not going to go over the technical details for that, but I'm happy to chat offline or also refer you to the paper. Okay, any questions before I talk about implementations? Yeah.
So what was known before your work? Because you said the data structure was invented previously, right? So in terms of the approximation.
Yeah, so the data structure was invented previously. The authors did not use it to solve the k-core problem. It was used for densest subgraph, as well as graph coloring, if I remember. Yeah. Okay. So implementation details. So we implemented this algorithm for multi-core machines. We use parallel primitives and data structures from this graph-based benchmark suite that my collaborators and I worked on a couple of years ago. How do we store the neighbors of these vertices in the data structure? So we use concurrent hash tables to store the neighbors. And for a given vertex V, we have one concurrent hash table to store its neighbors at or above its level. And then we have a separate hash table for every level I below the level of V to store its neighbors at that particular level. So you might wonder why this is not symmetric here. Well, the reason is that in our data structure, we have a bound on the number of up neighbors that a vertex has, but we don't have a bound on the number of non-up neighbors or down neighbors, so to speak. So our hash table for storing the up neighbors is going to be bounded in size, but if we were to store all of the neighbors below us in a single hash table, that hash table would just be too big. And when we're doing operations on the data structure, things would not be work efficient. So that's why it's not symmetric here. Okay, so, oh yes, question.
I'm not sure if you're aware of this, but this data structure by Jensinger and others, there is a distributed algorithm, actually from, I don't know, 15 years ago, by Berenbaum and Elkin.
Berenbaum and Elkin.
Yeah, that works in a logarithmic number of rounds, and it gives basically the same result. When I plug in rounds, you can get this level data structure.
Yeah. So what was it used?
Distributed MAS and coloring and a bunch of things in vulnerable velocity graphs.
I see. Yeah. I mean, I think we looked at that, but if I recall correctly, like the bound it gave us was not exactly what we wanted. But it was a while ago. Maybe one knows.
Yeah, is that data structure for maximum arbitrary, or is it for
It's
the
this
current arbitrary?
layer data structure, but same.
Yeah, is that data structure for computing the maximum arboricity over the course of all updates, or is it for the current arboricity?
So distributed algorithm, it's not a data structure. And the goal of this algorithm is to compute such a level data structure, but they don't call it level data structure. Because they're not maintaining anything, they're just computing it in logarithmic number of rounds. And yeah, I think that many people in this community are not aware of distributed algorithms. This is why I'm mentioning it. It might be worth checking into.
Yeah.
Thanks for that.
Yeah, cool. Yeah, we'll check it out. I think we looked at that. I don't remember exactly what the conclusion was, but yeah, thanks for pointing that out. Cool. Any other questions? Okay. Okay. So like moving these vertices around in the PLDS, like moving them up and down levels, it requires us to carefully update these hash tables in parallel, and also for work efficiency. Okay. Let me just briefly go over the complexity analysis. The span is easy, and the work is complicated. So I'll talk mostly about the span, and then give you some intuition for the work analysis. So the data structure has order log squared n, number of levels. And recall that in our batch deletion algorithm, we need to compute these desired levels, which is the closest level below it that satisfies the lower bound invariant. So we basically use a doubling search here. So we check one level below 2, 4, 8, and so on until we get to a level that does satisfy the lower bound invariant, and then we do a binary search within the last interval. So it's order log of the number of levels, which is order log n span for each level. And then for the hash table operations, we just plug in a black box result, so you can do everything in order log star and span with high probability. So this gives us a total span of order log squared n log n with high probability. The work bound, we got order b times log squared n amortized work for a batch of B updates. This is based on a potential argument. Uses a very similar analysis to the Bhattacharya, Hensinger, and Nankai and Surikakis paper from 2015. We made some slight modifications, but the high-level idea is the same. And the vertices and edges here are storing potentials based on their levels in the PLDS. And these potentials are going to be used to pay for the cost of moving vertices up and down. One thing that we needed to do is we needed to argue that the operations that we're doing in parallel can be mapped to an equivalent set of sequential operations. And once we do that, then we can basically just reuse the sequential analysis there. Okay, experiments. So we ran experiments on 2 types of Google Cloud instances. The first one is a 30-core machine with 2-way hyperthreading with 236 gigabytes of memory. We also used a larger machine with 48 cores and 2-way hyperthreading with over 1 terabyte of memory. We only used the larger machine for some of the larger graphs that needed it, since I didn't want to pay that much for using it for all the graphs. This is a lot more expensive, the second instance. So we test on 3 different types of batches, insertions, deletions, as well as mixed batches of both insertions and deletions. The results were pretty similar, so I'm just going to present the results for the mixed batch setting. Okay, so we compared 4 different implementations. PLDS is the algorithm I just described. PLDS opt is an optimized version of PLDS where we tweak some of the parameters such that we no longer got a 2 plus epsilon approximation. The approximation was a bit higher, but it's a lot faster. And then as for existing work, Hua et al. Presented a parallel exact dynamic algorithm for this problem. And Sun et al. Presented a sequential approximate dynamic algorithm for this problem. And as far as we know, there is no other algorithm that's parallel and approximate for dynamic K-core besides PLDS. Okay, so here we're plotting the average time per batch versus the average error. So we're averaging over the errors for all the vertices in the graph in terms of their Coreness estimates. On the left, we have DBLP, which is a small graph with about 2 million edges. On the right, we have LiveJournal, which is a larger graph with 85 million edges. Okay, so the 2 axes are in log-log scale here. So first, we can look at Hua. So Hua is this black line. The reason why it's a flat line here is because it's an exact algorithm. So it doesn't incur any error, so we just care about the running time. The blue dots correspond to PLDS opt. The red ones correspond to PLDS, and then the green corresponds to the Sun et al. Implementation. So one thing to notice is that if we fix the average error that one of the blue dots achieves, it actually gets the fastest running time across the implementation. So for a given error that PLDS opt is able to achieve, it gets the best performance. However, note that the PLDS and Sun implementations are able to achieve slightly better errors than PLDS opt, because as I said, PLDS opt changed some of the parameters so that we don't have the 2 plus epsilon guarantee. But actually, in practice, the PLDS opt implementation is able to get errors as low as 1.25x. So this is already better than the 2 plus epsilon approximation guarantee that PLDS and Sun are able to achieve. Yes.
I mean, you mentioned that it's difficult to parallelize the exact algorithm. So what do Black Hawk?
So this is not a theoretical result. So their algorithm actually has linear span per update. They get a little bit of speed ups in practice, which I'll talk about in the next, I think, in 2 slides after this. Yes.
And what is the approximation ratio that Sun et al. Achieve?
Yeah, so Sun et al. Also get a 2 plus epsilon approximation.
And what update time do they have sequentially?
Yeah,
Polylog?
it's order log squared and amortized per update.
Okay. And they prove the approximation ratio independent of your approximation ratio? Or?
Yeah. So they, in their proof, we actually found a slight mistake, which it was kind of hard to fix. So we came up with a different proof. Yeah.
What kind of batch update that you generate?
Sorry.
How do you generate the update?
Yeah, good. So we tested on graphs a whole bunch of real-world graphs. Some of them had a temporal order to them, meaning that the edges had timestamps on them. So for those, we just processed the edges in the timestamp order. And then for the other graphs which didn't have timestamps on the edges, we just like randomized the edges and then generated batches based on that.
Is there a theoretical guarantee for this PLDS opt? You said it's like slightly worse than 2 plus epsilon.
I mean, it's actually, I think it's actually a lot worse. It is bounded by some constant, but I don't remember what it is right now. But it should be a lot worse than the 2 plus epsilon. Okay, so overall, we're able to get like 2 to 3 orders of magnitude speed up over Sun et al. Sun et al. Is sequential, so part of the speedups just come from being parallel, but we also get additional speedups just from better optimizations in our implementation. And then compared to the exact parallel algorithm of Hua et al., we get up to 25x speedup. Okay, so here are the scalability results. So here we're varying the number of hyperthreads and looking at the average time per batch. PLDS opt and PLDS scale pretty well. Sun is sequential, so it's flat as expected. Hua et al. Actually, like they get a little bit of speedups, but not much. And the reason is because exact K-core is hard to parallelize. They have some BFS, DFS process in their implementation, which is it can be very, it could have very high span in many cases. Okay, so overall, our self-relative parallel speedups are pretty good. 33x for PLDS opt on average. PLDS gets about 26x on average. But Hua et al. Only gets a little over 3x. Okay, and the PLDS opt implementation is faster than all the other algorithms when you just use 4 or more cores. We also looked at runtime versus batch size. And again, PLDS opt is able to get the fastest performance across all of the different batch sizes. Okay, and we get between 2.5 and over 100x speed up over the Hua et al. Implementation. We also compared the runtime of the batch dynamic algorithm to parallel static algorithms for K-core. The first one is an exact algorithm that my collaborators and I worked on many years ago. And then in this paper, we also came up with a 2 plus epsilon approximate K-core decomposition algorithm, which is static and also parallel. So here I'm looking at the speedups of the batch dynamic algorithm over the static one using a batch size of 10 to the 6. The graphs here are ordered by size from left to right, smallest to largest. And we see that we get speedups for almost all of the graphs. So for all of them except the 2 smaller graphs, YouTube and DBLP. For the smaller graphs, it turns out that the number of edges they have is not too much larger than the batch size. So in that case, it actually makes sense to just rerun the static algorithm. But once you get to larger graphs like Twitter and Friendster with over 1 billion edges, this batch size of 10 to the 6 is pretty small compared to that. So we're able to get speedups of over 100x. Okay, so let me conclude. I talked about a theoretically efficient and practical batch dynamic K-core decomposition algorithm. Using the PLDS, we are also able to get parallel batch dynamic algorithms for several other problems. So low out degree orientation is sort of a trivial corollary of the level data structure, but we also looked at maximal matching, clique counting, and graph coloring. The graph coloring result is a parallelization of a recent paper by Hensinger et al. The source code is available online if anyone's interested in checking it out. And that's it.
Questions?
So actually, I had one question. Are your data sets available somewhere publicly, these graphs that you used?
Yeah, so the data sets, they come from this Stanford Network Analysis repository, so they are publicly available. We just downloaded graphs from that website.
And the way you made them dynamic is as you sketched. So you don't have a specific repository for the dynamic versions of the graphs that you used?
No. So like for the data sets that had the temporal information on them, we just used that. Like this information was in Snap. And then for the other ones, we just randomized the order of the edges.
Maybe it's a dumb question, but, oh. I mean, since my little familiarity with this, there's these people in database world who have like really honed the sequential static algorithm, approximation. Have you run it against sequential, non-dynamic, static algorithms?
Oh, sequential. Yeah, we have compared with that, but unfortunately, I don't remember the results off the top of my head. Like when we came up with the parallel static K-core algorithm like many years ago, we compared with the static one. I don't think like our single threaded time was too much off from
the new ones too, right?
Sorry.
There were new ones.
Oh, there are new ones. Yeah. I haven't looked at the new ones, but if you can send me a pointer, that would be great. I'd be interested in taking a look. Yeah.
Other questions? No? So thank you very much again.
All right. Thank you.